Hello. Okay, this is going to be chapter 1, section 3, which is about slope fields and solution curves. I guess we should actually call them graphical solutions. Okay, so let's go to, well, I guess we should do a quick recap. So last time we talked about, look, in special cases where the derivative is only dependent upon the independent variable, let's say x, you can solve by integrating. That, however, is not always the case. Sometimes your derivative is dependent upon both variables. So let me write this down. So let's say you have something like dy dx equals f of xy. So, well, what happens? Let's say you multiply both sides by f of x. And then you try to integrate. So here you get y of x equals, now what happens is that you're going to integrate with respect to x, but really what you need to realize is that this y in here, that's a function of x. So that function y depends upon x. You don't know what it is. So if you don't know what it is, how can you integrate to find out what it is? So it's like a chicken and the egg problem. You're trying to solve for y of x, but to solve for y of x by integrating, you would have to already know what y of x is. That ain't happening. So you're like, okay, I need to find another way to do this. So not solvable in general. So in this case, where this happens, in general, you're gonna have to come up with approximate or numerical or graphical solutions. And like an example of this would be, say, let's say you have your dy dx equals x squared plus y squared. So if you're going to integrate this, you'd get integral dy equals integral x squared plus y squared dx. So y squared depends upon x. To integrate it, you'd have to know what it already is. I can't do that. Boom, you're stuck. So what are we going to do? Well, we're going to try to solve this problem graphically with something called a slope field. So here's my graph. You know what y prime is. Y prime equals f of x. So let's say you choose some point right here. Some value x naught. So you have some point, x naught, y naught. So what are you going to do? Well, you're going to plug that x naught into f of x. So f of x naught is y prime at x naught. So that's going to, we're going to call that value m0. So at that point x naught, y naught, you can come up with some slope m naught. Now let's choose some other point right here. x1, y1. So if you plug x1 into f, you get the derivative at x1, which you can call slope m1. And you could do this for a bunch of points, and you would be able to see, like, oh, my function looks like this, because I know what its derivative is at all these various points. So you're like, okay, well, this, if you do enough of these points, you could put it together, and you get, like, oh, the graph goes through like this. You string together those points, because what happens is you start right here, you increment by the slope by that amount, you get to another point, you keep doing that, and you get this nice path. So you're like, okay, this is my approximate solution. Okay, so this is called making a slope field. And let's look at how this works. Doing it by hand is a real pain. Instead, what we're going to do is we're going to use Wolfram to do this. So I'm opening up a Mathematica. 1 second. So we're changing windows. There we go. Okay, cool. So let's define our f of x, y. So let's say that our let me go back to the other one. Sorry. Oops. So let's come up with a differential equation here. Let's look at the the population growth, which is called the logistic differential equation. The derivative of the population with respect to time is equal to k p m minus p. So this is called the logistic equation. Okay, so what this is telling you is that the rate of change of the population is the dependent variable. The rate of change of the population with respect to time, the dependent with respect to the independent, is proportional to the population times the difference of m minus p. So m is called the carrying capacity. So the idea here is the carrying capacity is the maximum possible population that you can get. So your rate of change of the population is what the current population is, or it's proportional to what the current population is, times how far away you are from, like, this is the most amount of people that we can feasibly have. So let's plug in some numbers here. Let's say you have dp dt equals 0.0004 times p times 150 minus p. So in this case, what's the most number of people you can have? 150, 150,000, 150 million. In fact, is whatever your units are, it's 150. So let's say you can have at most 150 people in some environment, because that's like the most people you could support given the food and all that. Okay, so the rate of change of the population is equal to the current population times 0.0004 times the difference of the max and what you currently are. If you multiply this through, you get 0.06 p minus 0.004 p squared. Okay, so let's look at the slope field for this. So we could say that this is our, usually we would write f of xy, but in this case it's our f of, our x is the independent variable, that's t. The y is the dependent variable, that's p. So my f of x equals 0.06 p minus 0.0004 p squared. Okay, so now I'm going to go back to Wolfram. Okay, so I'm going to say my independent variable is t, my dependent variable is p. Okay, and we get 0.06 times p minus 0.004 times p squared. Okay, there's a command to make the slope field for you. It's called vector plot. You give it the function. So we're going to vector plot tp, comma. Now what you have to do is you have to give it the variables that you're going to do this over. So one second, I have it written down, the order in which I have to do this, because I always forget. Make sure I do this right. One second. Oh, okay. So, sorry. The way you want to do this is, sorry, you don't put it in like that. What you're going to do is put brackets like this, 1, and then what you're going to give it is your function, the f of t p. Okay, so it's always going to be 1, comma, whatever your derivative is. And then comma, you're going to tell it the independent variable. In this case, the independent variable is t. Let's have time go from 0 to 100. And then you give it the dependent variable, which in this case is p. Let's have the population go from 0 to 150, right? Because the maximum population is 150. Okay, so here is this graph. So I'm going to copy the graph, and we're going to go look at it in OneNote. So I'm changing back to OneNote. Okay, cool. There we go. Let me paste this. Let's make it smaller. is this gives you an idea of the evolution of the system. So let's say you start off at time 0. Let's choose green with 60 people. You can see that it's telling you to sort of go this way. So you follow that curve. It looks like it's going like this, and then it's going boom, 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 boom. So what happens if you start off with 60 people, you increase for a while, and then as you get closer and closer to 150, your growth slows down. Okay? So I mean, that's just how that works. You start off at some point, it's like you're following some sort of stream of, right? That gives you your general solution. There's another version of this command that you can use, which is very similar, and it's called stream plot as opposed to vector plot. It looks very similar, but instead of a bunch of arrows, it actually shows you like a particular solution. So there's stream plot. So now you can actually see the individual solutions actually sort of connected. Let's go back over here. Let's paste it. Let's make it the proper size. So you can see we started off at, what was it, 60 around here. You can see, like I said, it follows it like so approximately. And it keeps on getting closer to 150, right, asymptotically. Oops, I didn't change over. There you go. I pasted the stream plot over. You can see I followed in green. I started at the 60 right there. Sorry. Right here. And then we followed it. It keeps on going bigger and bigger to 150. Okay. So this example was twofold. It showed you about the logistic equation. What is its meaning? And we looked at coming up with a approximate graphical solution by looking at this stream plot or vector plot. You can see we started off at some initial condition. Time was 0, population was 60. You can see over time what happens. It keeps on increasing to 150 more and more slowly. Okay. Now, before you go and have the computer graph everything, and this was a big deal when computers were very slow, and it might have taken days or weeks to have the computer calculate all this. Obviously, that's not as much the case anymore for the stuff we're dealing with, but it still is the case for like some stuff. You want to know about the existence of solutions. So you want to know, like, hey, given what I'm talking about, is there actually going to be a solution? And also you want to ask, like, hey, if there's a solution, is that the only solution, or are there other solutions? So this is called the existence and uniqueness of solutions. So let's say that you're given some derivative, dy dx equals f of xy. You're given some initial condition, y of a equals b. You want to know, hey, is a solution going to exist, and is that the only solution? Are there other solutions? Like, because if you look up here, you can see that there's only one path really to follow from a population of 60, and it keeps on increasing to 150. But what if it was also possible to go some other way? Like, what if you could have, like, what if it was possible to go down and decrease to 0? You want to know, is there that solution, two solutions, multiple solutions? Okay, so there's a theorem which actually tell you this, and it's called the existence and uniqueness of solutions theorem. So it says that if your derivative, f of xy, and the partial, oops, that's not partial. Where's the partial symbol? I know it's here somewhere. Ah, there we go. Oops. If the partial of f with respect to y, if the derivative and the partial derivative of the derivative with respect to y are continuous on a rectangle containing your initial point a comma b, there is a unique solution. So not only is there a solution, but it's the only solution. So what do I mean by this? You have your initial point right here, a comma b. You make some box that this is in. So let's say that you're able to go up and down epsilon in the y direction, and left and right delta in the x direction. So this is some rectangle which has x values a minus delta to a plus delta, cross b minus epsilon, b plus epsilon. Let's say that in that box, f of x, your derivative, and the partial of your derivative with respect to y are continuous. If in that box those two are continuous, then you have a unique solution. So in other words, it's worthwhile to graph and see what happens. And on top of that, it's worthwhile because it's the only solution. It's not like, oh, I'm going to have to look to see if the plot goes several ways. You look at it and you follow it, and there's only one way it can go. So let me show you how this will work. Okay, so let's say that you have x dy dx equals 2y. Okay, so let's divide both sides by x. Dy dx equals 2y over x. That's your f of xy. And so let's look at this. So is this function continuous? Well, it is not continuous if x equals 0. And let's also look at the partial of f with respect to y. So if you take the partial derivative of f with respect to y, you get 2 divided by x. Also not continuous if x equals 0. Okay, so what does this mean? If your initial point has x equals 0, you're not going to have a solution. But if you look anywhere else, yes, you will have a solution. And I'm going to go to Mathematica and have it do the stream plot, and you'll see how this plays out. So we'll do stream plot, put in 1, comma, our derivative was 2 times y over x. Let's have the x values go between minus 10 and 10, or minus 5 and 5. And let's have the y values go from minus 5 to 5. Let's copy this. Let's go back over to OneNote and we'll analyze this. Don't worry, I know that I haven't changed over. I'm just adjusting the size of the graph so that when we do go, we'll be able to see it. Okay, I'm switching over now. Okay, cool. Okay, so remember I said you're not going to have a solution if x equals 0. So where is x equals 0? X equals 0 is anything here. You can see that green line. So for instance, if you choose some point over here, such as like x equals 2 comma negative 2. Let's do it in green or red so you can see it. Here's a point right here, negative 2 comma 2. You can see that our solution gives you this sort of like parabolic looking thing that looks like that. So the graph would look like that. As you go through the x values, that's what the y values are. But what happens if you choose a point with the x value is 0? You can actually see there's these horizontal lines. Or like, I guess what you can see is that there's two parts of the graph. Let's choose another one over here that has a minus 2, minus 2. You can see that you get this other sort of parabolic shape. If you look at above the x-axis and below the x-axis, do you see how they're separated? If you start off with a negative y value, in other words, x not equal to 0, or sorry, if you start off with x not equal to 0, y not equal to 0, you can see that you get these sort of parabolas. Let me make sure that I say this right. But what happens if the x value is 0? So if the x value is 0, you can actually see there's sort of these, like, if you follow it, they're just pointing straight down like this. Okay, you don't get a solution there. You can see that everything is separated into two solutions. There's the ones below the x-axis and the ones above the x-axis, and they're like perfectly partitioned from each other. And you will not get a function which satisfies what you want if you start off with x equals 0. In other words, anywhere on the y-axis. Okay? Because there's nothing that happens, it just keeps going down. There's like a line right there where it just doesn't work out for you. So this is really useful because let's say that you can't solve it and you want to know if there's a solution defined by looking at the graph. You look to see whether there exists a solution. If there exists a solution, you're guaranteed that it is a unique solution if it fits these criteria. And that's all you need to know for Chapter 1, Section 3.